Hello, and welcome to today's webinar, How to Optimize Energy Costs, Reliability, and Sustainability in Central Plants. Our speaker today is Derek Supple. He's the Product Director for OpenBlue Connected Equipment and Optimization Products at Johnson Controls. Derek is responsible for product development of software solutions to help commercial and industrial facility owners reduce operating costs, improve mission-critical reliability, and reach net zero carbon goals. He joined Johnson Controls in 2008 and has served many roles, including National Sales Manager, National Account Manager, Energy Solutions Project Engineering Manager, and Sustainability Program Manager. He previously worked at Rocky Mountain Institute, MIT Lab for Energy and the Environment, and the Illinois Clean Energy Foundation. Derek's deep understanding of healthcare and utility plants make him a great speaker for today's webinar. Before we begin, it's important the audience knows Q&A is included, so feel free to submit questions throughout the event using the question and answer feature on your webinar toolbar. We have Mark Thompson from Derek's team here with us as well. He'll facilitate the questions. Derek will be sure to leave some time at the end of the presentation to address them. Please submit any technical questions using the same method, and they'll be addressed as soon as possible from our technical assistants who are in the background. The session will be recorded and available afterwards for all participants. And now I'd like to turn it over to today's presenter. Please go ahead, Derek.
Thanks, Lisa, and thanks all of you for making the time to participate in this Lunch and Learn. I've always enjoyed my participation in prior ASHE events, and this Energy to Care series is a great initiative. So thanks to you all for making the time to join. I'm glad to see so much interest in this topic with a great turnout in terms of registered attendees. So today we're going to talk about how to optimize your central utility plant to help reduce energy, improve sustainability, and improve the reliable operation to support your patient satisfaction and your Joint Commission accreditation goals. I'm going to try and stay as light on the theory and reserve as much time as I can on case studies and Q&A because that's what I get the most out of Lunch and Learns like this, and I feel the audience would the same. So as Lisa mentioned, we want to make it as interactive as possible, so please feel free to enter your questions along the way, and Mark will help me address those as we go through. So why do we care about optimization of central utility plants? So we work with many different healthcare organizations across the world. And there's kind of consistent themes we hear in terms of where their biggest challenges lie. They really fall into these three categories. First is labor shortages and knowledge gaps are a big problem. I think you all know the statistics. You've heard them many times if you're common participants in ASHE events on the aging workforce in healthcare facility management. The HFM and ASHE salary survey shows that the percentage of facility managers and technicians older than 55 years just continues to grow each year. One large healthcare organization we work with often says that 60% of their facility managers are over 60 years old. And those are the statistics, but for me, it really hits close to home. I can't tell you how often lately I've seen very specifically facility managers or key technicians at hospitals that we work with that have retired just in the last couple of years. And, when they leave, so much knowledge and expertise walks out the door with them. And yet the same, ASHE and HFM surveys suggest very few, 12% of healthcare facility managers have a formal succession plan in place. So that can lead to big knowledge gaps, a lot of key knowledge in particular about how to operate one of the more complex elements of your facility, the central plant, when that happens. The second kind of category is just if you're attending this Energy to Care, it's probably because you too are part of an organization that's one of many where we're witnessing just a huge push for more aggressive energy reduction goals, net zero carbon goals. And according to HFM magazine, most hospitals have set some type of carbon neutrality goal, typically 10 to 20 years down the road, and rightly so. I mean, healthcare facilities use a lot more energy per square foot than most other facilities. And if you added up all the healthcare sector globally and looked at just the carbon footprint or emissions impact, it'd be the 5th largest country in terms of emissions. So a lot of pressure on the sustainability and net zero front as well. And then last but certainly not least, energy savings is really important, but most healthcare facility managers we work with are very clear that reliable facility operation is most important, number one important. And that really is because it translates to patient satisfaction surveys, Joint Commission audits, and just overall, mission of the hospital, especially when it comes to mission critical systems like your central utility plant. Any downtime or unanticipated downtime that disrupts hospital operations in the name of saving energy easily wipes out, a year's worth of the energy savings. And so ensuring that reliable facility disruption is probably the highest priority for a lot of the healthcare facility managers we work with. So again, some pretty big challenges, just kind of setting the context for why does this matter? Why are we talking about plan optimization? So some pretty big problems, but technology is supposed to help us with all of this, right? Everyone's hearing about the digital transformation, and that's supposed to solve all of these problems, right? Well, we work with a lot of customers who have tried, and I think that's easier said than done. Many healthcare organizations have tried really hard to implement smart building projects to make their buildings smarter, more efficient, better patient satisfaction, but it can be a challenge. And so, these are some of the main reasons we see as to why it's a challenge to undertake some of these smart building analytics and optimization projects. We've always had a lot of data in our building systems. Buildings have long produced thousands of digital data points for decades, right? Every few minutes. But there's a few reasons why we maybe haven't put it to the best use. Not sure if this resonates with some of you, but who's been in a plant room or a control center that looks like this one. James Dice from Nexus Labs created this image, and it really resonated with me just to see, because we see it so often where you have all of these different siloed building systems, right? Each computer screen for a different system, right? And they're all isolated. Sometimes some healthcare campuses that serve, medical office buildings or different parts of the hospital have different automation systems. You could have a different screen or a computer for each different control system in the hospital. So we tend to have challenges around having siloed systems, data stranded in these different systems, not coming together. We've long had BAS alarms, but the last thing that we see facility managers needing is more alarms and a larger to-do list of everything that's wrong in the facility. Most teams know that they've got a lot of things to address and a growing list of deficiencies. The challenge is that the operators just don't have time to address it all. So we see alarm fatigue, and we see, unfortunately, still, I visit hospitals all the time with a variety of BAS vendors, JCI, Medisys included, where there's still hundreds of unacknowledged alarms. And so it's really, how do we take all this data that's coming at it and help the operator more proactively identify and use their time effectively. The other most common barriers we see tripping up, oftentimes the business case or the ROI for these types of smart building or optimization projects is, the systems aren't digital ready. There's either missing key sensors or maintenance has been an issue, and so faulty sensors aren't keeping up. Even if they do have the sensors, oftentimes they're not trended and saved. Really important to have long-term trends in place for setting historical baselines and being able to inform the business case for an optimization project. And then, the industry as a whole is making strides, but oftentimes even within an organization, you have different naming structures or tagging standards or ways of mapping what certain data points are and/or understanding actually what the control sequences are and how they work, because that's really important too. It's not just knowing what that sensor's point name is in the BAS, but understanding how it fits into the way the building was designed to operate. So some key challenges there, but a lot of potential to overcome those, and we're working with many organizations to do just that, to address some of those challenges we talked about at the beginning. This is a Department of Energy framework created by Hannah Kramer and the team at Lawrence Berkeley National Lab that I really like, that just helps you think about the hierarchy of needs for some of these digital building technologies, all of which can be applied as part of your approach to optimizing your central plant. So you have all these different data sources coming into a common data warehouse, and then this capabilities of needs starts with first what they call EIS, the Energy Information System, which is really about meter level monitoring, right? Hourly or hopefully, or even more frequently, and at the building level, but ideally also at the sub-meter level, to be able to see where all the energy inputs are going throughout the building. The next category is fault detection and diagnostics, which is about predicting poor performance of the building systems, diagnosing what's that true root cause, not just identifying that there's a problem, but what's the true root cause of the problem, and then helping the team really prioritize what are the ones to really spend their time on, so we're not just giving them a whole laundry list of other issues that they don't have time to address. And then lastly, for the focus and the real focus of today's presentation is going to focus on this last category of ASO, automated system optimization, otherwise known as advanced supervisory control. So you'll hear me use those terms interchangeably today, but what that means is having software technology that's continuously monitoring the overall system and running analytics or algorithms that then determine and send what are the best set points to then actually do real-time control to the system. So they're sending real-time set point commands to often the plant automation system to optimize cost, energy, carbon, or other types of objective functions. And what I liked about this study by the Berkeley lab team was, it's probably the most extensive study I've ever seen for measuring what the real benefits were at real sites. They tracked, I believe it was over 1 billion square feet of area over a 4-year period. They had a lot of different partners. Many of you probably were participants in their study, and they documented what was the true economics of applying these types of solutions. What was the level of savings and what types of paybacks did we see? And so, as you can see, typically for the EIS systems, the median building savings was about 3%. For fault detection and diagnostics, the median savings, whole building energy savings was about 9%, but it could really vary. And then they didn't have enough sites to really do a statistically robust estimate of median savings for the advanced system optimization. That's kind of a next phase of work. I think they're waiting to get more sites included as part of this study, but in our experience at Johnson Controls, we see an additional 5 to 20% savings, at least in central plant, from this automated system optimization type approach, above and beyond what you can get from the EIS and the fault detection and diagnostics alone. So there's a big opportunity there, and and I think what I like about this is approaching it in a comprehensive way, thinking about all three of these as you put together your roadmap for how do you make the most and get the optimal performance out of your plant. So why talk about central plant optimization is one of many different things you can do to achieve your energy and patient satisfaction goals, but it may be one of the biggest things, certainly from an energy perspective. So the 2018 Commercial Building Energy Consumption Survey, or CBEX, for those that know it, hasn't published their end-use breakdowns by facility type for types like inpatient healthcare, but I doubt it's changed much since 2012. This pie chart is based on the 2012 survey that was most recently published in 2019. And it won't surprise any of you to hear that HVAC is the largest portion of energy use in inpatient healthcare facilities. And certainly the biggest portion of that HVAC energy is the central plant. And if you just look at energy alone, electricity alone, cooling's about 23% of the average inpatient healthcare facility energy use. So if you're one that likes to use the Pareto principle or the 80-20 rule, focusing first where you can get 80% of the impact from 20% of the effort, focusing your smart building efforts on the central utility plant can be a really good place to start. The other trend that's important to think about when we're going into about how you want to develop your optimization approach and solutions is that you don't just want to think about minimizing energy use, although certainly energy goals, a lot of healthcare organizations have goals around minimizing the total number of BTUs, no matter if it's electricity, natural gas, et cetera. When you kind of normalize it all in units of energy use, that can be a really important goal. But oftentimes we also see that what the organization really cares more about might be the actual utility expense and the greenhouse gas footprint associated with that energy use. So not all BTUs are created equal. Some BTUs cost a lot more at different times of day than others. And so optimization can't just be limited to just getting the best, for a water-cooled chilled water plant, just getting the best kW per ton, or the best energy use over time is limiting the opportunity here, because we see more and more markets where whether it's utilities, governments, et cetera, are giving incentives for not just how much energy you use, but when you use it. That could be through peak demand charges, coincident peak charges, time of use rates. More and more areas now offering real-time pricing or demand response programs. And so it's important to be able to optimize based on what's the cost of energy now, and then how is it going to be different in the future. These are just, this slide shows just a couple examples in both a fully regulated, vertically integrated utility market like Southern California versus a market where customers can shop around for at least their retail energy supplier like Chicago. And the point is just to show, energy is only half the actual energy usage is only half the story. And that can often be, time of use pricing as well. But demand, both your peak demand and your coincident peak demand, right? How much demand you have at the system peak hours has a huge impact on your utility cost. And I think a lot of you, I'm sure, are very familiar, experts and know that, but even the ones that recognize that, it's easy to forget and just focus on the energy use piece. So it's important that to kind of transition from the energy optimization approaches of the past to true cost optimization, which is where more predictive approaches to optimization become really important. So we see a growing number of these ASO, automated system optimization solutions on the market, not just our own, that are bringing forward-looking capability to optimize the cost over that future horizon, not just the energy efficiency. So in tackling your plant, you want to look at those three categories that the LB&L team talked about in their hierarchy, right? The first step is energy information systems, because you can't manage what you don't measure. And so what we've done here is kind of for a typical water-cooled chilled water plant, we just kind of set up a good, better, best framework for how you might think about getting the energy information systems or the sub-metering in place that needs to be there. Ideally, you want to measure all the energy input into the system and all the useful production of utility services your plant's generating, so you can see the true overall efficiency and not just the total system efficiency, but how each component is contributing to that. But totally understand that many hospitals just don't have that today yet, and need to go through a journey or a process over time to be able to get to that level. So the good, at a minimum, you want to at least measure and set up, again, as I mentioned before, long-term trends, really important for the production of chilled water, hot water, steam, et cetera, that you're delivering to the facility. And at least hopefully power for your largest users, your primary equipment, your chillers, your boilers, et cetera. Get the big ones right. Next level up, the better level is including accurate power readings for all the devices. Oftentimes, particularly when they're variable speed devices, you want that. And oftentimes that kW point is available from the variable speed drive. And then, of course, the best is measuring the energy inflows and outflows for all the equipment. So being able to measure not just electric power, but chilled water flow, condenser water flow to each device, and measuring that electricity with utility grade submeters on, at least on the largest high power quality meters on your largest energy consumers. So the second step, as you saw from the LBNL categorization of these solutions, is the fault detection and diagnostics, which is really about helping the facility operators stop being as reactive, always putting out fires, working on the latest problem, and start being a bit more proactive, from doing time-based maintenance to leveraging this technology to help prioritize the best condition-based maintenance. Some refer to this process as monitoring-based commissioning. I'm sure you've heard of that term. But we certainly, we're in the business of providing HVAC maintenance and controls maintenance for a variety of customers, and many of those customers are in the healthcare world are looking to us to do more condition-based versus planned maintenance or time-based maintenance. My point on the big kind of takeaway for me when it comes to fault detection and diagnostics for these plants is not all FDD solutions out there are created equal. Some fault detection packages out there are much more accurate than others. The big thing you want to avoid is the false positives. Oftentimes you can generate a lot of noise with false positives. And then it's not always easy to automatically, some of the FDD solutions stop after detecting the fault, but are weak when it comes to really automatically diagnosing what's the real root cause of that fault versus just listing 6 or 10 potential causes of the fault. And so that's something you want to focus on when you're putting together your strategy or your requirements for an FDD solution. And then lastly, it's just really important that the FDD solutions automatically help prioritize the faults based on cost impact, potential impact to critical patient care, duration, the fault's active, et cetera. Without that automated prioritization, it's just the list can become too overwhelming, and it doesn't really help that facility operator become more proactive, which was the original goal. This is just an example of just looking at one type of fault, which is the kind of easy to understand one, right? You have more system level faults as well as device level faults, but what's the impact of a temperature sensor that's out of tolerance by 2 degrees, 3 degrees, 4 degrees Fahrenheit? And you can see the difference in economic impacts of having that problem in an air handling unit discharge air temperature sensor. 3 to order of magnitude difference in the potential impact of that chilled water supply temperature sensor at having a 4 degree out of tolerance is more than 10 times the impact of the air handling unit sensor being out of tolerance. So this is where it's really good that these FDD tools, really important, I should say, that these FDD tools do a good job automating the prioritization of the faults. Otherwise, it becomes very labor intensive to kind of triage them and figure it out. And the best FDD approaches out there don't just use simple rules of thumb, cost to estimate the impact, but really accurately model the system level to get an accurate assessment of what the energy impact or the operations disruption impact could be, asset life, premature asset failure, things like that you want to use to quantify and prioritize those impacts. So lastly, we'll turn to the automated system operation, or ASO, the Advanced Supervisory Control Solutions, which, as I mentioned before, this is all about taking all that data that we talked about from all these different systems, weather data, et cetera, and then figuring out what's the best way to optimize the overall system performance. And there's a lot of different products and solutions in the market on this, but we kind of tend to group them into these 4 categories of approaches that we see healthcare organizations using to go above and beyond what they can get from just a standard plant automation system sequence of operation. So still see many sites that achieve very strong levels of efficiency and are optimizing their plants by experts, manual operation by experts that know that plant inside and out, have kind of honed their process to be able to achieve the best efficiency by really just understanding their plant. But obviously the challenge there is that only works when the expert is present, right? And they're not always going to be there 24/7. And back to the whole labor risk thing we talked about at the beginning, that can be a real risk if that's the approach. Advanced logic in your plant automation system. Oftentimes these are custom programs, either designed by a mechanical engineering firm or programmed by an experienced controls engineer, technician directly in the plant optimization. Sometimes at Johnson Controls, we refer to this as CPO Eddie, because Eddie was one of our top programmers who used to do things this way. This approach typically has a lowest implementation cost, but it's hard to scale because you've got a real dependency on the technician that put together that custom program and knows it. So for maintaining it over time as things in the plant change, the program often can't be very dynamic, right? And there isn't a lot of learning. It's kind of a static set of sequence logic that gets added to be able to do more advanced sequences for saving energy. The third category there is kind of a big improvement from the custom logic, which is more of a step and wait approach or an auto-adaptive approach. There is quite a variety of different optimization packages out there that use that type of approach, where they make a small change and then they measure the response. Did that small change improve, or did the overall efficiency improve or get worse as a result of that change? And then they kind of make a similar change in the same direction until they find that sweet spot or the most efficient place to operate. And so those types of auto-adaptive processes are nice in that they don't require a lot of computing power, right? Because you don't need to have a lot of data. You're just kind of reacting. And they have generated a lot of savings over the years. But the challenge there's 2 challenges with them. One is that they take time to find that best solution. And 2 is that they can find what we call local minimum versus global minimum, right? So that with the step and wait approach, if you're making an adjustment, maybe, okay, you're stepping, waiting, okay, actually my efficiency is starting to get worse now, I'm going to reverse back. And you end up finding this local minimum on the curve, right, versus a global minimum. And again, you should think of these as multi-dimensional performance curves that you're trying to solve for as part of this process. So again, they do require less computing power and less data or information to run because they can be more reactive, but they potentially leave savings on the table. And so the last approach we'll talk about is what's called model-based optimization. And so that's using a more predictive approach and using a model of the building, or in this case, the plant, and using math to really do an exhaustive search of all the different potential combinations of set points. And when I say set points, I mean both equipment selections and staging, binary set points, which equipment is on, which is off, and analog set points like temperatures, pressures, flows, et cetera, depending on how that plant is being controlled. And so using a model-based approach uses math to solve for what are those best set points that are going to minimize an objective function, which is often, energy cost to run the plant, could be carbon, could be other things as well. Sorry about that. So this is essentially a little bit more detail on how that model-based optimization works. As I mentioned before, it's pulling data from all the different, from their control systems, from meters, but also from weather forecasts. And in some cases, as we talked about, utility rates can be dynamic. So pulling in what's the latest day ahead or even hourly ahead utility rates, and pulling that all into this digital twin model of the plant that can then do this exhaustive search to find the right combination of which equipment to run to meet loads at the most minimum cost over that future time horizon. So the difference here again is, rather than using control logic rules, the approach is letting the math do the work to find that solution. And the benefit also is, rather than having static rules that may be programmed into a controller sequence, we can, as you see, this process is more of a cycle, because the models and the algorithms can adapt and learn over time as conditions change. So for example, if a chiller's tubes are slowly fouling over time, the system may understand and adjust that the part load efficiency curve of this particular chiller has changed relative to the others, and so it may choose a different chiller to run as a result, and certainly alert the user that there may be a maintenance opportunity as part of a fault detection recommendation. And then the other advantage to this is that when you set like a minimum dollar value as the mathematical objective function, the approach can be very flexible to solve not just for energy in total BTUs, but different other goals you may have, right? If you put it all into dollars, the system can solve based on how you weight some of those different goals, things like water cost, peak demand charges, time of use rates, demand response revenues, and even potentially the cost of carbon if your organization uses that internally to quantify or justify the business case for investments. And this more math-based approach tends to be a lot more flexible. That's been, some of the approaches we used that were more step and wait, or these custom sequences would only apply for, the most common configurations of plants, but tend to get tripped up when you've got different unique configurations like a sidecar arrangement or a heat pump chiller, or a glycol loop for part of the system, et cetera. All the way, in my experience, every central utility plant tends to be a snowflake. They all tend to be a little bit different, and so this math-based approach can allow a lot more flexibility to apply these optimization methods to a lot more plants out there. Even plants having a mix of constant speed and variable speed equipment can trip up some of the other approaches, and this can be more flexible to that. So we're about halfway, which is great. So let's jump to some real examples here. And so for the case studies today, I wanted to show a mix of both kind of very small plants to very large and complex plants, because really these optimization approaches can have a strong return on investment and can apply across both. So we'll start with just a couple examples of some plants that are on the simpler side. These are hospital plants on the spectrum of roughly about 3,000 tons, 3 to 4 chillers. Both of these projects are ones where we're just in the early months of operation yet, so we don't have a full year of savings to report, but we're several months into the process, and just kind of picking a few examples just to show what the potential impact would be. This one on the left has been running in this optimization in automatic mode, where it's commanding the systems for several months. But what I'm showing here is just some findings from a short test that was done, in particular calling out here the energy, the average power, the average plant efficiency and cost per hour, just even of the cooling towers within this particular plant. You can see that prior to the test versus during the test and after, a significant difference in the amount of fan power energy as a result. So again, $3 an hour may not seem like a lot of savings, but that can scale, especially when you have multiple hospitals and those hours add up over time. The example on the right, again, kind of think a little bit more, one more chiller, right? combination of mag-bearing chillers and some traditional centrifugal chillers, variable primary system with variable speed, condenser water pumps and cooling tower fans. And in that particular example, we're on track to about 13% overall savings, which is about just over $36,000 a year in savings in that particular plant. So those are some simpler examples, but we know, like as I mentioned, every plant is a snowflake. There's always, some particular complications. Children's of Alabama is another example where they've really taken a leadership position in applying these types of plant optimization technologies. This one happened to be delivered through a broader utility services agreement or purchasing cooling as a service. But what's interesting about this particular story is they actually have two plants that serve the campus. They built the one in 2010, 2012 timeline as they did a major expansion, built a LEED certified expansion to the hospital. They needed additional capacity, had built this new plant. And then more recently, they had the McWane plant and the new CEP plant, and they were running at a baseline cost of about $1.8 million a year just for their central utility plants, which included the demand charges. They have a 90% summer ratchet during the months of June to September. And so what's interesting also about this one is that each of those two plants was on its own utility account, utility bill, had different demand charges, different ratchet, right? So you can't treat it all as if it's all going to one meter or one bill. And so as a result, the optimization needs to be able to optimize in the face of, the demand charges on both sides, on both plants. And part of the project was, in fact, to connect these plants. So the history is that the engineering division was trying for quite some time, but couldn't get this major project approved. They saw it to address many of the needs to improve some of their reliability goals and their energy savings goals. And the biggest cost was cross-connecting those plants, again, for both energy savings and better reliability redundancy. And so they wanted to look at some creative design options and leveraged a web-based simulation tool to look at what optimization could do if they connected these plants, to really see what would an ASO type solution give them. And it really helped provide a lot more of the detail, these simulations that they needed, partly to just to prove that they didn't need to increase the pipe size from 12 inches to 16 inches. And ultimately that helped them value engineer and save some capital dollars, 1.4 million in CapEx, which helped improve the ROI of the project, right? But it also gave them the data they needed to take it up and get the project approved through their board. So they, in fact, implemented that. They moved forward with the project that not only was connecting the plants, but converting from steam to hot water, doing a lot of coil upgrades throughout the facility, some full air handler replacements. Also, as part of that, enabling a higher design delta T for the plant. And then as part of the project, they also upgraded those controls in both of the plants and applied this automated system optimization type approach of software to the system. And so this is an example of what the results look like. Here's kind of a trend of how cooling load was being allocated prior to the project without optimization. So you have these three colors here. Each color is a different group of chillers. The blue is the centrifugal chillers in the new plant. The orange is the heat pump chiller in the new plant. And then the green are the chillers from the older plant. And so if you kind of look at how that load throughout the course of the year was being allocated there, and then look at the optimized approach, what you see is that you have a big increase in the orange line. I'll kind of toggle back and forth. So better usage of the heat pump chiller, as well as you can see much less usage of the older chillers that were in the older plant, the one in green here, over the course of the year. So this is just one element. Again, as I talked about, it's also about optimizing against those demand charges. Demand was a huge part of their bill, much like the example I showed earlier. So if we look at kind of the overall expected result, it's about $450,000 a year in annual savings. You can see they're actually planning to use more electricity, right? But the savings is really in the natural gas, and this helps, again, decarbonize, get off fossil fuel by doing more combined heating and cooling, and then also some significant demand savings there, as well as there is electricity savings in this 80,000, so they kind of add together. So there is a net electricity savings. We can describe more later, but kind of we break our savings down into what we call high-level optimization and low-level optimization in this case to get to those overall savings. So this particular project is still in the M&V measurement and verification analysis for the first year. That's still underway, but we can confirm that over the period we reduced the natural gas usage by about 70% versus the prior year period. So, and then lastly, we kind of going from simple and to somewhat more complex to most complex. So Stanford University Medical Center is served by the Stanford University Energy Systems Innovation, or SESI, Central Energy Facility. So it's a plant that serves both the Stanford University campus and the medical center. But I can tell you the energy operations team at the plant will tell you that their number one priority for this plant is ensuring reliable service to the hospital. Right? All of their internal customers are important, but the hospital is always the most important. They're the last to lose service in any sort of emergency curtailment event or something like that. This was a pretty innovative and historic project led by Stanford, obviously affiliated engineers, AEI, Whiting Turner, ZGF, and Johnson Controls was a partner as part of the team, which was really a major project to replace a campus cogeneration system at the end of life with the latest generation of district energy, low temperature, hot water, et cetera, and optimized energy with energy storage and really it was designed as part of an approach to really how do we best meet the university's needs over the next 50 years. So in a 50-year life cycle cost assessment was looked at to compare different designs and figure out what's going to enable net zero carbon the best, right? But most cost effectively over that period. Serving a health care organization, this plant's also subject to the California Office of Statewide Health Planning and Development, or ASHE requirements, right, which is another important consideration to any sort of optimization project. Overall, the plant serves about 70 million ton hours per year of cooling and 2.2 million MMBTU per year of heating load, hot water load across the campus, including the hospital. So this one is while there's not a ton of equipment, it's a lot of large equipment in the plant. What makes it complex is the storage dynamics and the utility rate and real-time pricing type dynamics of the system. So as you can, kind of some of the key features of this plant are 3 2,500 ton heat pump chillers, heat recovery chillers. You can see there's also 4 centrifugal chillers, and then there is a hot water generator for the cases where they do need to use some natural gas to complement the heat recovery plant to meet the heating needs of the campus. But then also very visibly apparent when you go to the plant is the very large thermal storage. There's about 10 million gallons of chilled water storage that can hold about 90,000 ton hours. And on the hot water side, it's about just over a 2 million gallon hot water tank, which is about 600 MMBTUs of hot water storage. So, and the chart at the bottom is just showing kind of the opportunity, particularly in this climate zone, but it can be something we see pretty consistently across different climate zones. Is there's a huge opportunity for heat recovery. Initially, before doing simulations using this optimization tool, the Stanford engineers thought the opportunity to be modest, but you can see there's quite a large overlap where the campus needs both heating and cooling. and that overlap corresponds to about 75% of the time there is that overlap, and 93% of the campus heating and hot water needs can be met through waste heat from the cooling needs of the system. And so obviously major investments were made in both the plant, these plant equipment, the thermal storage, and the distribution systems out to campus, but they're complemented by the automated system optimization, or ASO type software approach, to really get the best bang for their buck out of that investment in this plant of the future, if you will, and all of the storage assets along with it. So what you can see here is what the advanced controls can deliver when combined with these types of storage assets. The first plot shows the campus electricity use in red, and then the total Stanford electricity use in orange. So it's a plant versus campus. And basically what you want to contrast between the pre-optimization and the optimized dispatch is we're really able to manage those peaks, drop the peak significantly from 43 megawatts to 36 megawatts, or a 17% reduction in peak demand. And because demand is such a big part of their overall utility bill, that and some of the energy savings from the system adds up to about $500,000 per year in savings versus what was already a very efficient, very highly modern plant design. So those are some of the examples, and we have many more which we're working on and excited to share in the future. Just doing a quick time check here. We're almost there. Just want to close before we get to questions with, how do you get started? What are some ways for you to start your journey? Or maybe you've already started your journey, but what are some ways you may be joining to hear what others are doing that might help you accelerate it or take your approach to optimizing your plants in your facilities to the next level? So some of the biggest we kind of paired up some of the hurdles we see with the solutions, right? One of the things we hear is that, things like this maintenance and energy optimization aren't attractive investments. And so one of the tips there is sometimes by just framing it in terms of a simple payback, you're not going to be able to compete as effectively with other investments the hospital finance team may be considering. Make sure to present it in metrics they use to evaluate other investments like ROI, net present value, or what's the impact to the operating margin of the hospital, and not just what's the simple energy payback. Energy savings may not always be the number one priority for a lot of healthcare organizations. So make sure that you're not just only quantifying that in the business case. Look at the non-energy benefits of these types of strategies around avoided unplanned downtime, less emergency repairs, extending the asset life, and make sure that's part of the business case as well. We understand everyone's got limited budgets. That's one of the challenges, right? You can't do optimization unless your automation is working. And if you have a lot of automation system deficiencies, valves that aren't working, et cetera, then it's hard to optimize. And so in those cases, we recommend just try and break that journey down into phases, right? You don't have to do it all as one project or all in one fiscal year necessarily. Work through an approach to get the plant to be optimization ready first, and then you're gonna have a really solid ROI to apply these sort of optimization approaches. And then make sure you're linking, these projects to the patient care and the comfort. Link the business case to your HPS scores. And then the last, common hurdle, a lot of the plant engineers or facility managers want to do optimization here is, well, if it's not broken, we don't want to fix it. But when you think about it, if you're failing to plan just because something's not broken, you're planning to fail. So make sure that you're taking a more proactive approach to bring all of these different types of, again, energy information systems, fault detection, and this advanced supervisory optimization together into a strategy that's really going to help you achieve your energy goals and improve ultimately the patient experience, which is the most important thing. With that, I think I'm going to wrap it up and open it up for questions. What
Thanks,
questions
Derek.
do we have on here, Mark?
Yeah, we got some good questions in the chat here. First question is, when we were looking at the measurement and verification analysis of Children's Hospital of Alabama, you mentioned high-level optimization and low-level optimization. Can you give us a quick rundown of what those two different levels of optimization are?
Yeah, great question. So we trying to break the optimization problem down to simplify the math a little bit. The first step, what we call high-level optimization, is just our way of saying we're going to look out into the future and over time decide. Let's, in that example, right, where you had heat recovery chiller and you had these other chillers and these hot water generators, how much load do you want to allocate to those groups of equipment over the time horizon that's going to optimize the utility costs. So it's kind of that load allocation amongst groups of equipment over time, solving that optimal control problem over time is what we call high level optimization. And then once we say, that we want, the heat recovery chiller plant or the group centrifugal chiller group of equipment to produce 1,000 tons at this particular time, low level optimization just refers to doing the optimization of that system to get the 1,000 tons out of the overall that particular subsystem as efficiently as possible. So low level optimization is concerned with things like which equipment within that group to run, picking overall set points, analog set points to run. So it's kind of optimizing down at the device level within that system. And so in the children's example, we get savings from both. In some of the more simple examples I showed earlier, where maybe they have a constant utility rate that doesn't change year round, and there's really only one group of, there's only 3 chillers to choose from, really all of the savings are coming from that low level optimization.
Awesome, thank you very much. Next question. Does advanced supervisory optimization, is it only optimizing the set points, or does it actually command and control the chiller plant?
Yeah, so it's commanding and controlling the chiller plant by sending control commands to set points. But typically, the way we've seen it work best, there's different solutions that do this differently. In ours, we're still relying on a functional plant automation system. So we are really only sending in commands to change set points, and then letting the automation system do the rest, to do the PID control, if you will, to control that particular temperature system to a set point. So to answer your question, it's kind of a mix of both. We are turning things on and off automatically, but we're doing that by sending system level set points, both enable and disable of turning equipment on and off, and then the high level, the system set points for, say, like what condenser water temperature we expect to get out of the towers or something like that.
Awesome. Next question. When we talk about model predictive control, what kind of machine learning algorithm do we use to encompass that strategy? Sure.
So really the machine learning is in two fronts. One is, as you saw earlier, a big part of this is not just optimizing for the now, but optimizing for the future. So one element to model predictive control is being able to predict some of those future inputs. How much load is there going to be in 2 hours, in 4 hours, and even tomorrow, or even 3 days from now, right? If we're trying to plan for whether we want to charge or discharge a big energy storage tank like at Stanford. So one element of machine learning is learning based on the past to be able to predict the future loads. And we also predict utility rates in some cases as well. So being able, for example, to take the weather forecast and then look at the day of the week, the time of day, campus schedules, other events, other inputs, et cetera, and determine, for this particular hospital, what's the load going to be at this time. So that's one element of machine learning. And then the other is more, as I mentioned, this digital twin of the plant really is, think of it as just a system of all these different multidimensional efficiency curves that are being used to solve for what's the best combination of equipment to run. And so the other machine learning algorithm is around updating and adapting as those those models change as the true performance of the equipment changes, maybe from what the manufacturer's rated performance is, learning from that and changing the control optimization control commands as a result.
Thanks, Derek. Next question. Is advanced supervisory optimization, is it typically vendor agnostic? Meaning, would it matter if I had one or more different types of building automation system vendors in my plant, or let's say I had multiple campuses with different BAS vendor controls? Is this a solution that can sit on top of anything?
It's a great question. So there is quite a mix out there. I'd say there's definitely solutions, and certainly the OpenBlue central utility plant from Johnson Controls is agnostic, and there's several others that are and can sit on any system. There's also a lot out there that are kind of only work if you have that particular automation system.
Thanks. And while we're talking about building automation systems, some of our hospitals are very restricted from their IT in terms of this optimization, perhaps residing in the cloud or off-premise. How does advanced supervisory optimization tackle things like info security from IT in their policies?
That's a really good question. Yeah, IT is a really important partner to work with as part of these. And, we see a lot of healthcare customers that are taking advantage of the cloud-based applications, but there's still, especially when you kind of go from that analytics and dashboards and insights, and fault detection to actually taking real-time control of the mission critical equipment, right? A lot of times a lot of our healthcare customers we work with, or at least their info security teams, they really want to see those applications running inside the organization's firewall, right? Whether that's a data center as part of the hospital, or at least part of that healthcare organization's network, versus coming from a vendor's cloud-based solution. So we fully expect to need to be able to support customers with this analytics and this optimization, both at the edge, right, on premise or in the cloud. Certainly helps to be able to at least, connect to some of these external factors like weather forecast or utility rates coming in. So in most cases in the healthcare sector, we haven't had a lot of resistance from the info security folks being able to at least connect to the internet to pull that sort of information in. But yeah, to your point, there are still sites that want to be more air gapped and at least have the control application running within their network.
Next question here, probably have time for two more. If a hospital does not have enough trend data for 1 year to go through the modeling exercise, does advanced supervisory optimization, can it still work? Or what ways can we pivot around that hurdle? And this would also apply, I suppose, for new construction facilities as well.
You bet. Great question. So it can still work. We don't need the 1 year of data necessarily to learn or to train the models like other AI approaches might. So there's not this learning period, because we're building more of a physics-based model in taking a lot of the manufacturer specifications for that equipment. As long as we've got all the data, we can start optimizing right away. I think the value of having that long-term trend data is really to inform the business case more so than to impact the product working. Certainly getting some of it might help the product do a better job optimizing, or the software do a better job, but really the value of the trend data is to understand where are you today really, in terms of how much you're really spending, how much opportunity is out there. So that's where that baseline trend data can be really important. It gives you a kind of a starting point for your business case. And again, even if you don't have it, there's ways of extrapolating from a small data set, right? And at least coming up with a pretty good model of what your baseline usage is if you don't know what it is.
Thanks, Derek. Last question here. As you said, advanced supervisory optimization can work in Edge, but you need a lot of memory to run a control application like this in the Edge controllers. how do we exactly handle all of this advanced supervisory logic that we'll need to optimize the system?
So yeah, typically we run it, it can run on potentially an industrial appliance, but typically we run it on a server at the edge just because of the amount of data coming in. But the good news is, the cost of a virtual server continues to go down, right? It doesn't need its own dedicated physical server necessarily. It can share with other facility-related applications that are also running on your network, right? So, and the cost of data storage continues to drop. So typically in those cases, we work with the IT infrastructure team supporting facilities to put it on an existing virtual server.
Thanks, Derek. So that puts us right at time. I wanted to turn it over to Lisa for our closing statements. Thank you all for joining today.
Thank you. I'd like to give a big thank you to both Derek and Mark. A recording from today's webinar will be emailed and also shared online. Thanks again for joining the webinar today, and I hope you all have a great day. Bye, everyone.